All right, thank you for coming back for the next session of today's lecture. I'm sure you are very excited to talk about Arrhenius acids, but keep it down. Okay, let me do the talking. So, what is an Arrhenius acid? These are the type of acids that are formed from the donation of a hydrogen ion to water. So, typically, you can consider this scenario as dissolving a substance in a container of water. If the substance is ionic, it's going to release hydrogen. The hydrogen will attach to the water molecule and form what we call hydronium. Hydronium has the chemical formula of H3O plus. And an acidic solution is a solution with a significant concentration of the hydronium ion. So some of the characteristics of acids are their taste. They're typically sour. They turn litmus paper from blue to red, and they react with bases. Okay. Here's a depiction of that type of chemical reaction. When HCl dissolves in water, hydronium ions, as I mentioned before, have the chemical formula H3O plus, and chloride. Now chloride, that suffix tells you that it's negative. These are produced from this chemical reaction. So here's hydrogen chloride. It mixes with water. In the process of dissolving, the hydrogen is attached to the water molecule, forming hydronium, and the chloride is liberated, forming a chloride ion. So we know that typically solutions of liquids have molecules which are very densely packed, but they have the kinetic energy to slide past one another. A solution of a strong acid has hydronium ions surrounded by negatively charged oxygens, which are present in other water molecules. So you remember how you have lattices that form from sodium chloride ionic compounds? Essentially the same type of electrostatic attraction occurs between the electronegative oxygen and the positively charged hydronium ion. Likewise, the chloride ion, which has a negative charge, is surrounded by positively charged hydrogen ends of the water molecule. So why is this? In chapter 5 we talked about different type of compounds, right? You have ionic, covalent, polar, and covalent nonpolar. Water is what? Covalent polar. It means it has an unequal distribution, therefore most of the electrons are surrounding the oxygen, and oxygen has a partially negative charge. Hydrogens have the partially positive charge. So those partial charges cause the molecule to generate partial charges, and therefore the interactions between positively or negatively charged ions in solution cause the water molecules to reorient into those directions. So you have many different type of attraction and repulsive forces going on in the solution, and they contribute to the characteristics of the solution. It's a little bit beyond the scope of this lecture. Let us discuss now the types of acids. You have binary acids. Binary, again, just referring to two elemental symbols in the chemical formula. Binary acids have the general formula of HX, okay? Now, the X can be pretty much any halogen. So, if it's fluoride, you have hydrogen fluoride, hydrogen chloride, and furthermore. A different type of acid would be the oxyacids. So oxyacids have the general formula HXO, right? And these will just be subscripts to denote different quantities of each of the constituents within the molecular formula. This is a chemical formula to represent what? Okay, I've already said it's an acid. And you see nitrogen. So let's refer back to some of our chemical knowledge. What is a nitrate? That's NO3. And if you have hydrogen, it will cancel out the charge, forming what? Nitric acid. Now, we call this nitrate, right? So anytime you convert a polyatomic ion from an 8 to a neutrally charged molecule, then you call that a oxyacid. So in this case, the hydrogen donates the +1 charge. Nitrate has a -1 charge. When the hydrogen couples with the negatively charged nitrate group, overall the molecule becomes neutral, right? So the 8 becomes the ick, you call it nitric acid instead of nitrate, right? So then what is this? We know this group is what? Sulfate. Sulfate has a -2 charge. If you were to add only one hydrogen, you would form what? Hydrogen sulfate. It's still an 8. You need to add one more hydrogen to form an oxyacid, excuse me. So oxyacids basically are 8s, are compounds which have oxygen within them that become neutral by adding extra hydrogen ions. Alright, so this is nitric acid and sulfuric acid. This is sulfuric acid. Okay, so organic acids. These are carbon-based. You have C2H3O2. Now, if it was just C2H3H4, if it was just C2H6, it would be ethane, right? But this is acetate, and with the extra acid, that makes it acetic acid. And this is what the chemical formula of acetic acid looks like. So you can see you have a lot of lone pair electrons on this region of the molecule. We already know carbon shares the same bond distance with the hydrogen, so this region of the molecule is typically very nonpolar. Okay, you don't care anything about that, but it's important to know that this region is electronegative because it helps you identify where the hydrogen is most likely to leave the molecule. I always tell you in chemistry the electrons are the functional group. So if you were to examine this region of the molecule, you can see that it would be very easy to abstract this proton by redistributing the electrons onto the oxygen, right? Because oxygen can have 8 electrons in its valence shell. So if it takes 2 electrons from hydrogen, hydrogen can only share 1. Then you would have 1, 2, 3, 4, 5, 6, 7, 8. Okay, so now we can identify this as the acidic hydrogen. This is the hydrogen that becomes released into solution, generating hydronium with the reaction with water. So these are different models that represent the same thing. This is your Lewis dot or the skeleton model. This is the space filling diagram, and this is the stick and balls diagram. Okay, so now we need to go into a different concept, because the question becomes how many hydrogens are released into solution. If the requirement is that you release a hydrogen into solution for it to be acidic, then you can classify different compounds based on the number of hydrogens they're releasing into solution. So either they're going to be monoprotic or polyprotic acids, right? Makes sense. So in each molecule of an acid, it can donate 1 hydrogen, then it's monoprotic acid. If each molecule can donate more than 1, then it's polyprotic. Straightforward, that's not complicated. A diprotic acid is something like sulfuric acid. We just discussed this, where it has 2 acidic hydrogens. If it donates both hydrogens, what does it become? Right, sulfate. Some acids, such as phosphoric acid, are triprotic acids. These are both polyprotic, but you can be much more specific in their cases. You didn't know you could learn so much about acids, right? Well, here's one more thing. You can classify them not only in terms of how many hydrogens are released, but also in their strengths. Now, what does a strong acid and a weak acid require for their definition? A strong acid is due to the complete reaction with water. So the strength of an acid is based on its reaction with water, right? Because we say that an acid is basically characterized as a material that forms a hydronium ion. So the more hydronium ions you form, that means you reacted more with water. Let's look at this definition. Strong acid, due to complete reaction with water, it generates close to 1 hydronium ion for each acidic molecule added to water. Okay, this is different for weak atoms. A weak acid, due to a reverse reaction with water, it generates significantly less. Okay, so this can also be used as a definition for electrolytes. What it's really saying is, if you take a molecule, does it break down completely and all the hydrogens become a part of the water? Do they all contribute to converting the water into an ion, into hydronium? And if that's not the case, it's probably weak. Another characteristic is the reversibility, because just like the hydrogen can leave something like hydrogen chloride, just something like acetic acid, just like it can leave, it can also return. So the degree to which it leaves but doesn't come back, that can also be contributed to the strength. So here's a weak acid to make my point clear. Acetic acid reacts with water and it's reversible. So although it forms a hydronium and acetic and acetate ions, this double arrow represents the possibility for a reverse reaction. So that makes it weak. The proton hydrogen is transferred to a water molecule. So we know that this is the acidic hydrogen, and this is what? Acetic acid. The acidic hydrogen is transferred to water, forming hydronium and acetate. And this can go both ways. So this is weak. Okay? And this diagram just shows that, it kind of shows why it's weak. You only have a few of the hydronium ions being produced. So it's pretty much going to be redistributing that hydrogen among different water molecules. Remember, it's the concentration of hydronium. So that means that plus charge on the hydrogen can be transferred not only to additional water molecules, but also to additional acetates. Okay? So this is visually difficult to recognize, but what it's saying is that every 250 molecules of acetic acid added to water, there's only about 249 which do not become. So most of the acetic acid, which is in water, only one acetic acid becomes a part of the ionic process of creating hydronium. So basically 1 out of every 250 acetic acid molecules will create a hydronium. You see how weak that is? Compared to hydrogen chloride, all 250 contribute to the generation of 250 hydronium ions. So this gives you a clear-cut definition of the strength of an acid. So sulfuric acid, when you add it with water, it creates hydronium. Now this is polyprotic, right? So although you transfer one hydrogen to create hydronium, it has one additional hydrogen which in a subsequent reaction can be used to protonate or add hydrogen to another water molecule. So you can see the type of potential that these types of acids have. So based on these properties, we can characterize the acids in different categories. The binary acids are strong, such as hydrochloric acid, but you also have some weak, like hydrofluoric acid. Oxyacids, these are the acids which they become neutral when you add a hydrogen, and some of them are weak. Organic acids, none of them are strong. And acetic acid is a type of organic acid. So names and formulas of binary compounds. Binary compounds have the general form of hydro, then you put the root ic acid, such as hydrochloric acid. So instead of saying hydrogen chloride, I can say hydrochloric acid. So let's go back to make sure that you're grasping the concept. This is names and formulas for binary acids. So we talked about binary ionic compounds, binary covalent compounds. Now we're able to describe chemicals in terms of their acidic properties. So you have binary acids, right? Binary acids, hydrochloric, ACl. We've also seen this as hydrogen chloride, right? So stick with me. So in other words, you put hydro representing the hydrogen, you put the root, which in this case would be chlor, right? And instead of chloride, you put chloric acid. The formulas are usually followed by AQ to represent the fact that it's in solution. Aqueous, aquatic, that type of familiarity. Names and formulas of oxyacids. So if enough hydrogen ions are added to a root 8, like sulfate or phosphate or nitrate, if enough hydrogen ions, are added to these polyatomic ions to completely neutralize the charge, the sulfuric acid is formed. So they're just giving you a roadmap. So if you have a sulfate and you add enough hydrogens to make it neutral, you form sulfuric acid. For example, nitrate, 8, the root is nitr. If you add enough hydrogens, in this case you only need 1, it becomes nitric acid. The sulfate has a -2 charge. You can see the trend, right? You add 2 hydrogens, you neutralize the charge, you balance the charge, in other words. 0 would be a neutral charge, so if I say neutralize the charge, that means take the charge to 0. And therefore you go from sulfate to sulfuric acid. Note that in the name for some reason. Okay, phosphate, same deal. So chemical nomenclature. The general procedure for naming compounds, so you need to look back at chapter 5 to look at table 5.5. Okay, you need to basically just decide what type of compound the name or formula represents. So if you have an ionic compound, it's going to be different than an acid, than a binary acid. And that's going to be different from a binary covalent compound. And secondly, just apply the rules for writing the name, the formula. So make sure you look at the tables, make sure you look through the chapter, and take some time to go through the tutorials because they're very helpful. They help you go from describing the formula to generating a name, and then also looking at the name to generate a formula. So that's going to pretty much conclude today's lecture. Please be aware there's some homework problems inside, and if you have any questions, please feel free to contact me. All right, you're free to go.